bet goes something like this. I'm willing to pay a certain amount every month for the next 10 or 20 years. Let's say it's a 10-year term policy. I'm going to pay a certain amount every month, and if I die, you'll pay my beneficiaries whatever the nominal amount is, let's say $500,000. So the question is, what should the insurance charge you? Now, if they charge you too much, you say this is not worth it. So they're going to charge you for $500,000. If they're going to charge you $10,000 a month, you say that's not worth it. But if they're going to charge you $500 a month, is that worth it? And because it's a competitive industry, there are going to be different people, different companies bidding for your business. And in order to decide from their point of view whether it's worth doing this, they need to have an estimate of the probability that you will survive the next 10 years. And there may be different groups of people. So firstly, it depends on your age. How old are you now? If you're 20 now, the probability that you'll survive the next 10 years is much higher than if you're 70 or 80. If you're in good health and your blood pressure's okay and everything's okay and you don't drink and you don't smoke, then you have a higher probability than somebody who has high blood pressure or smokes or does something else. That's a mortality risk. So they find out that sort of stuff, and then they build these life tables. So they're extensive life tables for humans, and in humans there's a huge sample size. So they got all the data. They know when you were born, they know when you die, and historically they've got this information, and so they collect this data, and then they can mathematically estimate that in a population of 10,000 people, let's say we have 10,000 people age 20 today, how many will live 1 year, how many will live 2 years, how many will live 10 years. So you construct what's called a life table. So a life table consists of these numbers L subscript I, which are the proportion of individuals alive at exact age I. And the life table can start out with, you can say, okay, at birth, they're L0 individuals. And some life tables, especially human life tables, may be quoted. You can get books of these, or they're produced by countries. They'll be different for different countries. They're different for males and females. They may have other classifications of individuals. They'll be different for people who have high blood pressure versus low blood pressure and those sorts of things. And so you get an aggregated group. If you hear an insurance company say, you do not need a medical in order to get this insurance, you know that their statistics include all these healthy people, unhealthy people, and they're going to charge you more. So you don't want to buy insurance like that. You want insurance that says, we're going to check you medically, and we're going to try and put you into the A1 group, which are the healthiest individuals, and then you'll pay less because the life table for that group has better statistics in it. Now, some life tables, you might say, if we start off with 1 as a proportion, then all the numbers will be proportions. So, for example, L0 may be 1, L1 may be 0.97. That means 97% of those people in the sample are alive at age 1. So 97% survived. L2 might be 0.93. So you can say 93% of the individuals survive from age 0 to age 2. What proportion survive from age 1 to age 2? So we'll call that S1. S1 is the proportion of individuals that survive from age 1 to age 2. So how do I work that out? Yeah? Yeah. So this is equal to 93 divided by 97. And in particular, if we go down and we have Li individuals, then Si is equal to Li over Li plus 1. So those are the proportion that survive the next year. Oh, yeah, sorry. While you were on your way, we discovered our error.
Okay, so you guys know.
Yeah, so it's working now, sorry. Thank you. I feel very bad. It's good for your life insurance. Okay. So this is one of the basic columns. This is a derived column. So there are all kinds of derived columns. So for example, the column, like if you're age 20, what's the probability that you'll live to age 30? So if you've got an insurance company and you're age 20, they will take L20 and they'll put, this is Li plus 1 over Li. They'll take L30 and L20 and they'll calculate that probability that you'll make it from L20 to L30. And then they'll use that. So they'll have a look. They'll do a complicated calculation. They'll say, if you start paying them now a certain amount every month, by age 30, they would have collected a certain amount of money from you. They will turn that to a present value calculation. They will then calculate the probability that you will die during this period. And if you die, when you die, how much they'll have to pay you out. And they'll do a present value calculation. And then they'll say, okay, we need to make 10% on this. So then they'll take 10% of the number and they'll make sure that whatever they expect to pay out, they're going to get in 10% more from you. And you're willing to pay that 10% because what's at risk is not just for that 10%, you're buying peace of mind, so that if something bad happens, you're willing to pay for that. You're willing to pay for that service. That service is to give you peace of mind, so that if something happens, then your family will not be left out in the cold with no resources, and it'll be a great tragedy for them. Okay, but we're going to talk more in the context of data that's appropriate to biological populations. So in biological populations, we don't have very refined data like we have for humans. In humans, we're collecting this data all the time, and we can calculate quite precisely what these proportions are. However, there are certain assumptions that are made. And these assumptions relate to how you collect the data. So there's something called a horizontal life table, horizontal, and a vertical. A vertical can also be known as a cohort life table. So there are two different ways of collecting data. You can either collect it horizontally, which is sometimes also called latitudinal studies. It's also called static. And it relates to the fact that if you look at individuals today, if you're 20 today, what's your expectation that you'll live to 30? Well, that's different than if you were 20 200 years ago, 100 years ago, 50 years ago. Things are changing all the time. And in some senses, actually, longevity is now peaking and it's getting worse again. So it's been getting steadily better. The probability of making it to 90 has been going up for the last 100 years. Now that's turning around. Why is it turning around? Is it turning around? I've heard stuff about it. I haven't seen definitive data, but people think that the probability that you'll live to 90 is not necessarily as good as your parents living to 90. Why is that? Yeah. Okay. Well, it's not so much poor diet, but the increase in carcinogens in people's environments so that rates of cancer go up. Rates of cancer go up because we have a lot of additives to our food, but we also have a lot of carcinogens in our environment. Our environment is not as healthy as it used to be. And it was pretty bad in the 19th century when you lived in the city and they had smokestacks and they were burning all kind of crap in the air and the air wasn't very clean. But if you lived out in the country where there's clean air and sea breeze, you were okay. Now, of course, we're completely altering our environment so much. There's a lot of stuff in our environment now that we can't get out as easily. Certainly, a lot of our city air is cleaner than it was 30 or 40 years ago. So that's good news. But there are a lot more additives and chemicals that we use and that we come across every day. A lot more pesticides that are used to produce our food. All these may ultimately reduce longevity. But here's an interesting life table. So this, and this is a life table for a dinosaur. So you can say, how could you possibly get a life table for a dinosaur? Okay. Anybody have any ideas how you can get a life table for a dinosaur? Fossils, yeah. So you can look at fossils, and from the fossils, you have to make a lot of deductions. Presumably, there are people who say, we can age the fossil. We can say that whether this is a 2-year-old dinosaur or a 4-year-old or a 6-year-old. It may not be that easy to do that, but scientists have never been hesitant to go out and speculate and to make assumptions, and based on those assumptions to try and do some science. But if you have a living population, you can collect the data in two kinds of ways. So what I can do is I can do an experiment, and people do this, for example, with fruit fly. They rear fruit fly in cages, and they get 1 million fruit fly. And then they say, okay, these fruit fly have just hatched. They can look at the hatching rate, but then they can look at the number that have hatched. And for every 10,000 that hatch today, how many will be alive tomorrow, the next day, and so on. So fruit fly, you don't use years. You use days. And it turns out that the average fruit fly may live for 30 days, 100 days, whatever. So their day is more like our year in terms of longevity. And so you can do experiments with fruit flies, and you can follow a cohort of fruit flies that you rear in the laboratory. And you can say, if I give fruit flies, well, let's rather get to mice, because that's sort of a little closer to humans. Not much, but a little closer, actually a lot closer. And so you rear 10,000 mice in the lab, and then you feed them on two kinds of diets. And they've just found out that if you give mice grapefruit, they're actually healthier than if you don't give them grapefruit. Who saw that study on the Berkeley website? So you can have a life table for mice feeding on grapefruit and those not feeding on grapefruit, and then you can deduce that the expected lifespan of a mouse on grapefruit. Now, for mice, you'd have to go for a couple of years. So you'd have to stretch this experiment out, let's say, for 2 or 3 years. But you can do it. But now say I wanted to collect a life table for elephants. Would that be a good way to do that? What's the problem? They live for too long. So, here I am at the start of my career. I'm a PhD student, and I'm going to build a life table for elephants. And I go out and I look at, in this park, I go to a place like Kruger in South Africa, and identify all the newborn elephants there. And then every year I come back and I say, how many of these elephants? So this would assume that I could find them. It would assume that I could count them, and then I could count every one. Let's say magically I could do this. Well, I have the technology. It's now 50 years from now, and I can label them each, and I've got GPS data and everything. Then you could build this for elephants, but if your PhD would have to last like 60 or 70 years before you got a reasonable life table, because that's how long elephants live. So there is another way. Instead of doing it in this following a cohort or doing it in this vertical way, you can do it in a horizontal way. And in a horizontal way, you take a big population with all the ages represented, and then you say how many individuals of each age group that are alive today will be alive in 1 year. So you go to this population and you say, I've got a couple of, I've got 273 1-year-old elephants, and next year I count the 2-year-olds, and I've got 250, so I can see what proportion died. So in fact, what you're doing is you're estimating the probability of surviving at a particular age. So you're not measuring these directly, but you're measuring these indirectly, and if you calculate them all, then you can sort of back calculate. So here you have the L's, you can calculate the S's. But if I have all the S's, then I can set up equations to calculate the L's. And if you did that, then you would be building a horizontal life table. So in the studies where we look at individuals, we might build horizontal life tables for two reasons. For humans, we're not interested in a cohort that was born 30 or 40 years ago and trying to establish what their life table is. Because if I'm an insurance company, I want to know what's going to happen in the next 5 or 10 years if I'm going to insure somebody's life. And so I need the most up-to-date data. So what I would do is I would build a horizontal life table, and I would look at statistics of proportions of individuals alive in various communities and what proportions of them died by age. So I was looking at the proportions that died. I would have to know how many are there, and then I can calculate this life table that is relevant for today, because the probability that an individual age 20 will make it to age 21 today is different from what it was 20 or 30 years ago. And if you're an insurance company, you're insuring people not for 40 years from now necessarily, although you have to do some extrapolation because insurance companies will generally insure you for 10 years, and after or 20 years. Usually what they do is they give you a policy for 10 years, and then at the end of 10 years, they'll come and they'll adjust your rates based on new data. And when I bought life insurance over the last 40 years, I found that every 10 years, it's now costing less than I would have expected 10 years earlier, because the longevity of individuals has been increasing over time over the last many decades. So those are the two kinds of life tables. And if you have a life table like this, you can answer these sorts of questions. What fraction of dinosaurs died between ages 4 and 6? So you go to the age 4 number, L of t, over here, and you go to the age 6 number, and you look at the fractions that have died, and you can determine the fractions that have died between any of the ages, and you can plot L, and you can discuss its shape. So I'm not going to go over these in detail. You can go over them. What I want to focus on is this survivorship curve. So here we're plotting L of t against age in years. And so if we're looking at this dinosaur population, what we can see is that we started out with 1, and then by age 2, we were down to 0.6. So that's very common. In a lot of species of animals, the highest mortality rate is early on. And this was the case with humans until the 20th century. So if you read 19th century novels, or novels of things going on in the 19th centuries, who reads novels about 19th century society? Nobody. If you do, you'll find that it's a very sad time when children are always dying. Families would have 8, 10 children, of which 3, 4, 5, 6, or 7 of them would die. And everybody was very sad because everybody had some kids that, or many people had kids who likely died. Darwin, for example, had a daughter who died when she was young. And that always affected him throughout his whole life. So that was the state in which people existed. They existed in which it was quite common to have children die, especially in the first 4 years, when they're most vulnerable to diseases. Then usually once an individual, a human, is beyond 4 years, so if you have a look at your life expectancy when you are at age 0, and then you have a look at when you're age 4. When you're age 4, in those days, your life expectancy was higher than at 0. So at 0, when you were born, your life expectancy might have been, let's say, 32 years. And when you were 4, it might have been 43 years. You can say, how can that be? Well, that's because they had a high probability of dying in your first 4 years, which would have brought your average way down. So there was a high proportion. It's like today, in societies, in parts of Africa, they say the life expectancy of an individual might be 37 years, especially where there's large death rates due to HIV/AIDS. But those individuals who are dying of HIV/AIDS are sometimes dying in the early 20s. And by the time you get to 30, your life expectancy is no longer 37, it may be 55 or 60. It takes a huge jump. So these are the kind of information that you get out of life tables. Now, when you draw a life table, or when you draw a curve like that, you're plotting L of t against time. So here's time, and here's L of t. But what I'm going to do is I'm not going to plot L of t, but I'm going to plot the natural log of L of t. This is called a semi-log plot. So there are plots called log-log plots, and there are plots called semi-log plots. A semi-log plot is one. Excuse me, I don't allow people to. Yeah, I prefer you watch my lecture. Even if you are looking at this on your tablet, that's okay. I prefer it, but then I know. So please close. Yeah. It's only because I don't know what you're doing. If I knew what you were doing, I'd be fine with you looking at the lecture online, but then I don't know what's happening. Okay. So why would I do this? The reason why I do it is to help clarify certain ideas about mortality rates. If, for example, if example L of t was equal to e to the minus RT, so that was when t is 0, L of t is 1, and then it follows an exponential decay. What happens if I take the log of this? The natural log of L of t then is equal to the natural log of e to the minus RT, which is equal to minus RT. So if I take the log of something that has an exponential decay, then when I take the log, what do I get? If I call this variable y versus t, what kind of line do I get? What is this? It's just a straight line. So it means that this is slope minus r, where r is positive. So this is a negative slope. So on a log-log plot, if there's an exponential relationship, then it means that the mortality curve becomes a straight line. Now, what does this exponential relationship mean in terms of the proportion that would die at each age? So this is kind of the rate that individuals die. So this is constant. It's not a function of age. It just is the number around decreases with time in a linear way, so that it's the same rate of decrease in each unit of time. So it means the proportion that are dying each time unit is the same. Are there natural populations where you would expect that to happen? What do you think? Where the proportion that die in each unit of time doesn't change with age. Bacteria, yeah, that's a possibility, sure. Okay. What about something more charismatic? Unless you consider anthrax charismatic. Huh? Squirrels, did you say? Yeah, so why would you expect that? Yeah. Yeah. Yeah, but why? Why would you expect that in birds and squirrels? That it wouldn't? So when they're very young, you may not expect it, but when they become adults, if it's not age dependent, then it means that there's some external thing that's catching individuals irrespective of their age. So a certain proportion are like falling to predation. Yeah? Right. So usually we would expect, if the main cause of death is disease from aging, so this is not infectious disease, this is disease from aging, then you'd expect that it would, as individuals get older, it becomes more and more likely to die. But if it's from predation, then you would expect that if the predator is an efficient predator, it can't only catch old individuals, it can catch healthy individuals as well.